Hello gems, welcome back to another video of the one shot 1 hour series. In this video we are targeting the chapter current electricity. Okay, in the previous two videos we have already targeted chapter 1 and 2 of your 12 standard. So if you are interested in that, do check out the links in the description box of this video. Okay, so with that being said, I would request you to set aside this hour of your life and let's get this done. So the first topic that we will be dealing with today is electric current. Okay, so electric current, as you might know, is basically flow of charge, right? And we choose the direction of the positive charge to be the direction of electric current. Okay, so suppose we have applied a voltage across a conductor, electrons will flow, right? So there is a electric field set up in the conductor and electrons will flow. Okay, so suppose we assume that the electrons are flowing in this direction. Okay, electrons are flowing in this direction. We can assume physically equivalent system where the positive charge is moving along that direction. Okay, it's the same thing. If you say electron is moving along this direction, or you can say equivalently positive charge is moving along that direction. Okay, so conventionally we choose the direction of the positive charge to be the direction of electric current, not the direction of electron. Okay, so whatever the direction of the positive charge, that is the direction of your electric current conventionally chosen. Now as I'm speaking of direction, you might wonder that electric current is a vector quantity. No, that is not the case. Electric current is a scalar quantity. Okay, it is defined completely by its magnitude. You don't need the direction. This is something which is chosen by convention for us to help. This is not actually the vector direction. Okay, or rather you can say that your electric field, electric current will not follow any vector laws. Okay, it is completely defined by its magnitude. If you see, if we have electric current along this wire I1, I2, same wire, you can twist and turn it. Okay, now according to vector law, the I3, the net current, should be along this direction, right? I3 should be along this direction. But if we twist the wire in some other sense, the current will flow that way. Okay, basically means that it does not follow any vector law. It is a scalar. Okay, it will only exist as in how you shape the wire, right? It will be along the wire, not how it is defined to be according to the vector law, because it is a scalar. It does not follow any vector laws. Okay, so SI unit of electric current is amperes, which is denoted by capital A. Some books might also use I, but we will be using A only for the unit. Amperes. Okay, it's a huge unit actually. You will see usually current in the form of microamps. Okay, so yeah, that is something to note. And you can also define 1 ampere as 1 coulombs per second, since electric current is nothing but rate of flow of charge, right? Flow of charge, so Q by T, so coulomb per second. Okay, now you can define it mathematically as I is equal to dq by dt. This is usually used when you are supposed to find instantaneous current at a particular instant. Okay, suppose you are given q as a function of time, or I as a function of time. Okay, so as a function, whenever you have the charge or the current as a function of time, the best definition to go for is the instantaneous one. Okay, you can find the instantaneous current by taking the derivative of your charge. Okay, so and in other cases, suppose you are given that this much amount of charge is flowing in this time interval, then you are supposed to go for the average average definition. Okay, suppose you are given 5 coulomb of charge is flowing in 10 seconds. What is the current? So you can find the average current. Okay, and suppose you are given q as a function of time, q is equal to something t square, something like that. Okay, so in that case you can differentiate. Okay, we'll come to one problem which will make things more clear. You can also find the amount of charge when some current is flowing. So using this definition, you can see it is current is differential of charge. So charge is integral, and integral I dt, which means area under the IT graph. So suppose you are given a graph of current versus time, then whatever the area under that curve is, that is the amount of charge that is flowing in that interval. Okay, you can also find the amount of charge by the average definition. So in this case, the current should be constant. Okay, so you can find the amount of charge as I times delta t. If the current is constant, you can directly use this definition. If it's not constant, you go for the integration method. Okay, if it's constant, you just multiply the whatever the constant value is with the time interval. Okay, let's come to two types of current. Basically, there will be DC current and there will be AC current. Okay, alternating and direct. Okay, the direct current does not vary in time. Okay, it will have a constant magnitude, constant direction. Okay, excuse me, sorry. AC current is generally periodic. It does vary in time or maybe in direction, okay, or maybe in both. You'll learn more about this in the upcoming chapters. Okay, currently we are only focusing on DC current, okay, with the one which does not vary with time or in direction. Okay, so let's come to this problem. Here we are given some current as a function of time. Let's say during something, and you are supposed to find how much charge passes through this conductor in this time interval, 5 seconds to 10 seconds. Now current is given as a function of time, so you can use the integral format. If current was constant, you can directly use this. Okay, now current is not constant, it is a function of time, so we'll be using q is equal to integral I dt. Now the limits you know, t1 to t2, right? So 5 to 10 seconds. Okay, so let's integrate this. So we have integration of 4 plus 2t square dt from 5 to 10. Okay, so we get 4t plus 2t square. So 2, what will we have? 2t cube by 3, right? T square is t cube by 3. Okay, and this is simply 4, so 4 dt integral is t. Okay, so from 5 to 10, don't forget about the limits. So when you substitute, so upper limit minus lower limit, right? So substitute upper limit, so 40 plus this is 1000, right? 10 to the power 3, 1000, so 2000 by 3 minus lower limit. So substitute the lower limit, this will be 20 and plus 5 cube is 125, 125 into 2 is 250 by 3, right? So here if you solve this further, we'll get 40 minus 20 is 20, and 2000 by 3 minus 250 by 3 is 1750, right? 1750 by 3. Okay, if we solve this further, what will we get? Let's check it. The answer over here is 603.33 coulombs. Okay, of course, everything is in SI units. The current is in amperes, then this is in seconds, so your charge will be in coulombs. Okay, this is the answer that you get. Over to the next section. The topic that we are discussing today is electric current. Okay, the theory behind it and what is causing it. Okay, so you might wonder, you already know it. Since you are applying a supply voltage, you are creating a potential difference. Okay, you are creating a potential difference, you are creating an electric field. Okay, electric field, there will be force on electron. F is equal to QE, chapter 1, right? So force on electron making the charge flow, electric current. Next chapter. No, that is not the case. Okay, so here it is described via drift velocity. Actually, when you apply the electric field, you might wonder that electrons are accelerating. Okay, that is not the case. You'll see that electrons are moving with a constant speed. Okay, we'll come to that. For now, let's see briefly what is there in solid conductors and electrolytes, which is causing the electricity to flow, which is very simple. You know that in solid conductors, basically the metallic ones, you have a sea of electrons, right? The valence electron can move throughout the entire surface of your metal. So we have free electrons. The valence electrons are not tightly bound to the atoms, so they can move over the bulk. Okay, so this bulk movement will cause electric current. Okay, so there is a potential for electric current, that is what I am saying. And even in electrolytes, you have positive and negative charges. So suppose you have salt, sodium chloride, and you dissolve it in water, so it breaks into ions, sodium and Na plus and Cl minus, right? So these ions can potentially cause electric current. The motion of these ions can cause electric current. Okay, so let's study the actual theory behind your electric current. This is how NCERT describes it. Is it 100% correct? I doubt. Okay, so the theory is that basically at room temperature you will have random motions of electron, which is at very high speed, 10 to the power 5 meters per second. Okay, so basically since this motion is random, okay, the net flow of charge is 0. Okay, one charge is moving like this, other one is moving like that. Okay, so it is random, completely random, and this thermal motion is actually cancelling out in between each other. Okay, so the net flow is 0, and hence there is no electric current at room temperature. Okay, since you have not applied any potential, there won't be current out of nowhere, right? But what happens when you apply the potential? When you apply the potential, you see the flow of electrons, right? Opposite to the direction of electric current, electric field, okay, and electric current, of course, okay. So here you have applied the potential, there is electric field over here, okay. You also see the flow of electrons, and you might see that, you might feel that the electrons should be accelerated opposite to the direction of electric field. But that is not the case. What happens over here? Let's study that. So the electrons do not accelerate. You might wonder, F is equal to QE. There is force on electron, they should accelerate, but actually they suffer frequent collisions with the ions and your atoms, okay, which are there in the conductor, okay. Besides the electron, there are also atoms, right? So they are constantly colliding with them, okay. You'll see a term relaxation time in the next section, okay. So basically there are collisions, okay. So collisions between the electrons and the ions, okay, or the atoms, okay, in case of your solid conductors. So these electrons will not be accelerated, they will lose basically their kinetic energy to these atoms, okay. Since they lose the kinetic energy, they actually tend to move slowly and steadily in the direction of your in the direction opposite to electric field, okay. So this constitutes a drift velocity, somewhat a constant velocity with which the electrons are flowing, and this is of the order 10 to the power minus 4, and this constant velocity is giving rise to current, okay, not the accelerated motion. The accelerated motion is not very sufficient, is not sustainable, okay. It's constantly colliding and losing kinetic energy, and it moves basically at the end result is that it moves with a steady velocity, which is termed as the drift velocity, okay. This is an important term. We'll also see an expression for it. It is of this order, and this theory might not be completely correct, okay. So there might be a lot of videos on YouTube about this, but we'll stick to this since this is what NCERT prescribes for you, although it's wrong. Whatever. Let's move to the next section and let's see some important relations having to do with your drift velocity. So coming to topic number 3, here we will be discussing different relations having to deal with your drift velocity, which you just learned. Okay, so first of all, we'll see what is relaxation time. It is basically the time between two successive collisions, okay. So between two consecutive collisions, okay. So basically for the electrons, okay, we know that electron is frequently colliding with the atoms and other electrons or ions, okay. So you have to define a time, okay, relaxation time, the span for which it can relax, okay, between any two collisions. So once it collides over here, the time that it can get for relaxation up till it suffers the next collision, okay. So first collision, then relaxation time, next collision, okay. So the time for relaxation basically free of collision, okay. So relaxation time is the time between two successive collisions, okay. So first collision, relax, second collision, okay. So that time in between was the relaxation time. It is generally very small, okay, 10 to the power minus 14 seconds, so small, okay. So that is what I mean by frequent, right? Electrons suffer frequent collision, and that's why there is loss of kinetic energy, and you can assume that electron is drifting with a constant velocity, okay. Now the expression for drift velocity is given as E tau by m. Tau is relaxation time, E is your charge, right, and m is the mass of the particle. Here electron, so mass of electron, okay. E is electric field, capital E, okay. So that is how you define your drift velocity, okay. This is an expression that will derive in the next class. The derivation class is kept separate, right? So the derivation series is separate for those who don't know. We also do one shot derivation series, so that is separate. We'll be deriving all these relations in that class, okay, which is next class on 2nd November if I'm not wrong, okay. So that is the expression for your drift velocity. Now you can also find a relationship between your drift velocity and electric current, okay. So it is given as I is equal to NEAVD, okay. N is the number density of electrons or the particles, okay, number density of charge. How is that defined? That is defined as number of charged particles, number of electrons divided by the volume, number by volume, okay. That is the density, right, mass by volume. So number by volume will give you number density. Okay, and here we have E is electric charge, as you know. A is area, cross section area. Okay, current is flowing through an area, so that cross section area. Vd, drift speed. Okay, relationship between your affair between your electric current and drift velocity. Okay, you can also define it in terms of current density. So density is basically current per unit area, right? Current flows through a cross section area, right? So current per area is density. So basically taking this I on the other side, you get J is equal to NEVD. Okay, we'll be deriving this in the next class. Now mobility is a new term. Okay, it's defined as the itself defined as the ratio of Vd by E. Okay, how free is your charge in the system? Okay, so that is mobility, mobile, free. Okay, so that is defined as Vd by E. Okay, it has the unit meter square volts per volt second. Okay, you can derive it from here, since your electric field is volt per meter, right? And this is Vd is meters per second, right? So we'll reach up over here. Okay, so let's calculate the drift speed now. We'll use study one numerical based on this. So we are supposed to tell the drift speed of an electron. Current is given, 1 ampere current exists in the copper wire. You are given the cross section area, the number of free electrons. These are the number. This is number of electrons in 1 centimeter cube. Okay, so you can find number density. Now you are supposed to find drift speed. You are given current. So what relation you'll use? They are fair, right? So you'll use I is equal to NEAVD. Okay, area is given, E you already know, Vd we are supposed to find, I is given, and n small n we can find. It is capital N by V. This is number of electrons, right? The number of free electrons. Okay, so 10 to the power 22, and what is the volume? 1 centimeter cube. Okay, per centimeter cube. So 1 centimeter cube, centimeters to meter is 10 to the power minus 3. Sorry, 10 to the power minus 2, right? 1 meter is 100 centimeters. Okay, so 10 to the power minus 2 centimeters, sorry, meters is 1 centimeter. Okay, so this cube, right? So this is this many charge divided by 1 centimeter cube. So centimeters, 1 centimeter cube, centimeter cube. Okay, so here we'll get 8.5 into 10 to the power. So this will be minus 6. On top it will become plus 6. So this plus 6, right? This plus 6. So that will be 10 to the power 28. Okay, so now we can find Vd. Vd will be I by NEA, right? Vd will be I by NEA. So I is 1 amperes, N is 8.5 into 10 to the power 28. Now this is per meter cube. Okay, so standard way you always bring whatever is in centimeters in meters. Okay, so that you have a good time calculating. Okay, so then we have E. E is again standard in coulombs, know the value, and A, area, cross section area, 2 millimeter square. Okay, so 1 millimeter is 10 to the power minus 3. Okay, please remember this, milli is minus 3 and that is squared, millimeter squared, right? Area. So 10 to the power minus 6 it will become. Okay, 10 to the power minus 3 squared, millimeter squared. Okay, so it will become 10 to the power minus 6, and once you calculate this, you'll get 3.6 to 10 to the power minus 5 in meters per second. That's why we brought everything in meters. Okay, millimeters to meters, centimeters to meters. Okay, so that we get the answer, final answer in meters per second. Okay, in standard SI units. So you can see that your drift velocity is of the order of 10 to the power minus 5, 10 to the power minus 4, very less, right? So why is that? When you switch on the button, your light glows on immediately if the charge is flowing so slow. Okay, that is a fallacy of your drift velocity theory, I must say. Okay, or do explain me this thought in the comment section. Okay, the correct answer will receive a heart. Okay, so that's about this drift velocity and its relations and affairs. Over to the next section. Number 4, here we will be discussing resistance of a wire. You'll actually already know this. Resistance basically, as you have learned in your lower classes, is resistance to the flow of your charge flow, right? It is opposition to the charge flow. It is some intrinsic property of a conductor. Every conductor will have some resistance okay, which is due to the collisions between the electrons or some other factors. Okay, so basically the opposition to the flow of charge or to the flow of electric current. Okay, so resistance of a wire in terms of its length and area, resistance will be directly, it is denoted by capital R, so it is directly proportional to the length. Okay, so higher the length of the wire, the longer the wire, greater is the resistance basically, and greater the area, lesser is the resistance. Okay, so more the width of the wire, the area of the wire, then the charge can move freely about its cross section, right? So since the area is more, resistance will be less. Okay, so conversely, if the length is more, the resistance will be more. Okay, so directly proportional to length, inversely proportional to area. Okay, and the constant of proportionality is nothing but resistivity, which is constant for a given material. Okay, so suppose you have 1 centimeter of aluminium wire and 100 centimeter of aluminium wire, their resistivity will be the same. Okay, this is a constant. Resistivity for a given material is constant. Okay, aluminium, you only have to check that. Okay, aluminium, nature is same, resistivity is same. However, 1 centimeter of your aluminium and 100 centimeter of aluminium, your resistance will be different, right? Resistance is proportional to length. Resistivity is a constant. It is independent of the size or the dimensions of your material. Okay, it is only dependent on the nature of the material. Okay, so that is something you should remember. Now resistance denoted by capital R, the SI unit is ohm. It is denoted by that Greek letter, okay, like a cap, like a hat. Okay, resistivity, it is denoted by rho. Okay, and it is given, the SI unit is ohm meter, right? You can easily find it from here. Okay, area by length, right? Area by length. So this is ohm, area is meter square, length is meter, so that will cancel and you will be left with ohm meter. Conductivity is nothing but 1 by resistivity. Okay, so it has SI unit inverse of this, 1 upon, or ohm meter inverse raised to minus 1. Okay, so conductivity G, it can be also denoted by sigma, Greek letter sigma. You can write this that way. Okay, as I'm teaching Greek now. So this is sigma. So you can also define conductivity. It can be also denoted by sigma, okay, or G. It is inverse of your resistivity, 1 by resistivity. Let's come to this question. Let's see how much you have understood. Okay, so basically the major point I would like to stress over here is the area through which current is crossing it. Okay, it's the cross section area. Okay, so current is like this. You can see it's flowing in this direction, and A is the cross section area of this conductor. Okay, and length is basically the length that the current has to move. Okay, so keeping that in mind, let's come to this question. The dimensions of a conductor are as shown. Okay, you are given the dimensions. This length is A, this length is C. Okay, it's in plane, and the length that is going inside. Okay, this is the length, you can say. This is the height. This is the breadth which is going inside. It is B. Okay, you are supposed to find the resistance across AB, EF, and CD. Okay, across AB, which is this face and this face, top face and bottom face. EF, side faces, and CD is front and back. Okay, faces. And so let us find that out. Resistance across AB. Okay, resistance across AB. It is given that the resistivity of this material is rho. Okay, so is rho. Okay, so here you will have rho. And what is the length? Length across AB. Okay, length across, right? Length across AB is nothing but C. Okay, divided by area. What is the area? So cross section area. Okay, so we have the top face and the bottom face. Current is passing through the face. So the face area. Okay, what is the current is passing perpendicularly through the face. So that cross section area. So this cross section area. Okay, or the bottom face, you can see this cross section area, which is A is the length and B is the breadth. So area is length into breadth, AB. Okay, so if you didn't get that, follow me around for the second time, since we have to do it for EF too. So EF. Okay, so again resistivity is same material, rho. EF, across EF, the side faces. Okay, now what is the length? Length is the across width, right? So across. So the current will pass from E to F, right? So the length is AB. Sorry, length is A. Okay, it has to pass that entire length A. So length is A. divided by you can say what is the area. What is the area now? Area is the faces, right? The faces, if you side faces, if you see BC, right? B is the base and C is the height. So base into height, that is BC. Okay, ABC. Or finally, we can go for your CD, which is the front face. Front face, we can say rho, and the again you can go for it. It's easy now. The front and the back face. What is the length between them? Front and the back face. The length is B. So length is B, and we have the area of the face, right? Area of the face. So you can see AC, right, in this plane, AC. So those are your answers. I hope you are able to follow around. A is the cross section area, L is the length of the conductor. Okay, so that is about this section. Over to the next one. To topic number 5, here we will be discussing the temperature dependence of resistivity and resistance. Okay, so these physical parameters are dependent on temperature. Okay, so if you change the temperature, the resistance of the component will change. Okay, so you have to be very careful that your circuit is not heating any of the devices. Okay, if it's heating, then its characteristics might change. Okay, so suppose a resistor is heated, its resistance will change, and hence the result that you are expecting, you might not get it. Okay, so these quantities basically are dependent on temperature. Okay, so your resistivity is defined as M by N E square tau. Okay, so here there is no temperature factor, but you'll see that temperature affects one of these factors. Okay, one or more of these factors. Okay, so if you see this relation, we'll be deriving it in the derivation class. Your resistivity is inversely proportional to the number of charge carriers. N is basically the number density, as we have learned, and E is charge. Tau is relaxation time. So majorly you see that it is inversely proportional to your number of charge carriers and inversely proportional to tau. These two are constant, right? E and M are constant. So you focus on N and tau. So what happens when you increase the temperature? Okay, so two things happen. First of all, the number of charge carriers will increase. More electrons will have the energy to go in the valence band, maybe. Okay, sorry, in the conduction band. So more number of electrons will be available for conduction. Okay, so that is one change. Okay, so that will decrease the resistivity, right? N will increase, number of charge carriers increase, then that will decrease the resistivity. Okay, so the second thing that happens is there will be greater kinetic energy to these electrons, right? The electrons which are moving, since you increase the heat, and heat will increase the kinetic energy of this electrons, and as a result the relaxation time will go down. They will frequently suffer collisions. Okay, since there is higher amount of kinetic energy, they will randomly move about and hit on the atoms and ions more frequently. Okay, and that will make them lose the kinetic energy, and there will be basically more collisions. Okay, so the relaxation time will go down. So collisions increase, meaning relaxation time will go down. Tau goes down, meaning resistivity increases, right? It is inverse relation. Tau goes down, meaning resistivity increases. Okay, so these two things happen when you increase the temperature. Okay, one of them is decreasing the resistivity, one of them is increasing the resistivity. Okay, I will see two type of materials wherein one is dominant, wherein if you see the conductors, okay, let us focus on the conductors first. 2 is dominant. Okay, 2, this collisions will increase. Okay, this is not dominant in conductors. Okay, there are fixed number of basically your number of charge carriers, right, which are the conduction electrons. Okay, very much increase in the temperature will not affect greater number of charge carriers. Okay, so here the 0.1 is insignificant for conductors. Okay, the 0.2 is very much significant, because whatever energy you supply in form of increase in temperature will increase the kinetic energy and lead to greater collisions. So in case of conductors, the increase in temperature will lead to increase in resistivity due to increase in collisions. Okay, so that is the point you should remember. We'll come to this alpha. Alpha is positive for conductors. We'll come to that. For semiconductors, however, the second is important. Okay, sorry, the first case is important. Okay, here semiconductors have different, if it's doped, you have it significantly increases its conductivity. Okay, so when you increase the temperature, you can have more number of charge carriers. Okay, so this is more significant for your semiconductors. We'll be studying them in depth. This makes them usable at higher temperatures, right? So they are ruthlessly used, uh, almost used everywhere. What is that word? Ubiquitous. Okay, so in every of your electronic devices, right? So if you increase the temperature, your resistivity decreases, which is a good thing, right? So alpha is negative, we'll come to that. Okay, so here the point 1 is dominant, here point 2 is dominant. For now you focus on conductors. When we come to semiconductors, you'll understand why it happens. So they have basically charge carriers, they are working is completely separate. Okay, so now the relationship for the temperature dependence, resistivity at a particular temperature T. If you want to find resistivity at a particular temperature T, you should know resistivity at a standard temperature. We take it as 20 degrees Celsius usually, times 1 plus alpha T. Now alpha is this constant of your temperature coefficient. Okay, it's constant for a given material. Okay, and you just multiply it by temperature difference and add it to the original, basically original of your original resistivity. So that will give you the resistivity at a particular temperature. We'll be doing a question on that, so you'll understand how we solve this. Okay, so similarly, since the resistance and resistivity are directly proportional, you can also write the relation in terms of resistance. Resistance at a particular time t is equal to resistance at 20 degrees Celsius times 1 plus alpha t. Okay, here alpha is positive, meaning this graph will be linear, right? Linear and going up. Okay, with the increase in temperature, increase in resistivity. The graph for conductors will look something like this. Okay, so if you have resistivity and temperature, this is like y is equal to, this is some constant, right? Rho naught is constant at a particular temperature, 20 degrees Celsius, standard value of resistivity, and this will be varying, right? Mx plus c. So m is positive here, so it will increase. And for this, if you want the graph of rho versus t, as temperature increases, resistivity decreases. Okay, so this is the approximate graph for them. Okay, and alpha, now you get what is meant by alpha is positive and alpha is negative. It shows the nature of graph, right? Alpha is negative, decreasing, right? Slope is negative, slope is positive. Alpha is the slope of this graph, you can say it that way. Okay, so let's come to this. Here we have been given the resistance of a silver wire at 20 degrees Celsius. So this is R naught. Okay, so suppose you are not mentioned the standard temperature, usually take it as 20 degrees Celsius. Okay, this is the standard value. Okay, so in questions wherein you are not mentioned, take it as 20 degrees Celsius. If you are mentioned some different temperature, take that temperature. Okay, don't try to outsmart the system. So let's move ahead with the question. So it's placed in a liquid bath. Now the resistance becomes resistance at certain temperature. So we don't know the temperature of liquid bath. Now the resistance becomes 1.2 ohms. Okay, it increases basically. So you have heated it. Okay, the liquid bath is at higher temperature. What is the temperature of the bath? That is what we are supposed to find. Delta T is the difference over here. Okay, so let us solve this. You'll understand it better now. So R naught into 1 plus alpha delta T. Okay, we are using this formula. Okay, so R naught is 1 basically, so even if you don't multiply it, it's the same thing. Okay, here we have RT as 1.2, and here we'll have 1 plus alpha. Alpha for silver, it's constant for a material, is given as this, plus delta T. Delta T is difference in the temperature. Okay, T is original temperature and the temperature of the bath. Okay, so bath is at higher temperature, so higher temperature minus lower temperature. Okay, bath is at high temperature since the resistance increased, right? So T minus 20, T minus original temperature. Okay, so here you can subtract this 0.2 and we'll get 3.8 into 10 to the power minus 3 into T minus 20, right? So we can take this over here. When you solve this by this will give you around 52.6 in degrees Celsius, of course, this will be T minus 20. So you'll get the temperature of your bath as this plus 20, which is 72.6 degrees Celsius. Okay, yeah. So that is how you do it. I hope you were able to grasp this concept. It's very important. Dependence of your temperature, dependence of your resistivity and resistance on temperature. So that's about this topic. Over to the next one. So let us now briefly discuss Ohm's law and its limitations. Ohm's law, as you have learned in your previous classes, okay, it basically says that the potential difference across a metallic conductor will be directly proportional to the current flowing through it, right? So provided you keep the temperature and all other physical conditions the same, right? Because resistance is dependent on temperature. Okay, so we have to take special care regarding that the temperature and some other physical quantities are kept constant throughout the experiment. In that case, V, the potential difference applied, will be directly proportional to current, or you can replace this with equality, saying V is equal to IR. R is a constant over here, and it is nothing but resistance that we have learned, opposition to the flow of charge, opposition to electric current. Okay, R is constant, and you can also plot V versus I, right? In that case, you can compare this V is equal to IR with Y is equal to MX, okay, and you can see that your Y is V, I is X, then M, the slope should be the resistance. So the plot of V versus I gives you a linear line in most of the cases. In case of your usual resistance, it will give you a linear line, and the slope of that graph will basically give you your resistance. Okay, slope is equal to tan theta. So if theta is given, tan theta, which is also the slope, will be the resistance. The slope of VI graph gives you resistance. Okay, let's come to the limitations. The limitations are as follows. First of all, some components will not show linear relation. So in case of your basic resistor, carbon resistor, or the resistance boxes that you have, the graph will be linear. Okay, but in case of if you see diodes later in semiconductors, when we discuss them, their IV characteristics are remarkably different. Okay, it's not linear. Okay, so some components like the diodes will show you non-linear IV characteristics. So they are called non-ohmic. Okay, non-ohmic because they do not follow Ohm's law, or non-linear basically because the plot is not linear. R is dynamic, since we get a curve instead of a line. Here the slope is constant. In that case, slope is not constant, right? It will vary. The tangent will vary, right? The slope of the graph will vary at every point. Okay, so R is dynamic. R is changing. The slope is changing. The resistance value is changing at every point. Okay, so the example of that is a PN junction diode or other semiconductor devices. Okay, and also we can have one more limitation is that we can have different characteristics when you apply along different polarities. Okay, so such is a diode. If you use it in forward bias, the IV characteristics are like that. If you use it in reverse bias, you'll learn forward and reverse bias when we go to the semiconductor chapter. Okay, so in forward bias you have one characteristics, in reverse bias you have other characteristics. Basically, if you change the polarities. Okay, so if you change so if you have connected a resistance box in a circuit, if you change this to this, okay, so if you change this wire to that wire and that wire to this wire, so basically you are changing the polarity, nothing will change, right? Because resistance does not have some positive and negative. Okay, it will act the same way, but some device do have a positive and negative, and they act differently in forward way and in reverse way. Okay, your usual resistance does not do that, and they are ohmic devices, linear devices. These are non-ohmic devices. These are limitations of Ohm's law. It cannot cover up these devices, these components. Okay, now here is a question. Here you are supposed to find the relation between T1 and T2. These are two different temperatures, and we are studying the IV characteristics of a given material at two different temperatures. You can see that it is linear. Okay, it is linear at both the temperatures. You are supposed to tell the relation between T1 and T2. Is it greater than, less than, equal to what? Okay, so you can see that this is a IV plot, not a VI plot. VI plot will give you resistance as the slope. IV plot will give you 1 by R, right? what is 1 by, so V by I will give you R, but I by V will give you 1 by R. So IV plot, so here slope will be 1 by R. Now which slope is greater? Okay, we'll combine the logic of the previous section and this section together now. Now which slope is greater? You can see that slope for T1 is greater, right? The greater the angle, greater the slope. 10, 90, infinity, 10, 0, 0, right? So greater the angle, greater the slope. So 10 of this T1 is greater. Okay, the slope for the first one, so 1 by R1. So basically I can say slope 1 is greater than slope 2, right? So I can say 1 by R1, slope of the first graph, 1 by R1 is greater than slope of the plot, second plot, right? So now you can see that this is the relation that we obtain in R. What about the temperatures? Okay, or you can simplify this, we can say that R2 is greater than R1. Okay, R2 is greater than R1, meaning temperature, you know that for a conductor, okay, this is a metallic conductor, I forgot to mention. So for a metallic conductor, the resistance increases with increase in temperature. So R2 is greater than R1, meaning T2 is greater than T1. The temperature 2 will be greater than T1, hence the resistance has increased. R2 is greater. To satisfy R2 greater than R1, you should have T2 greater than T1. So this is the relation between temperature, T1 and T2. Okay, so that's about this section. Over to the next one. Topic number 7, here we will be discussing carbon resistors. First of all, you deal with two type of resistors mainly in your laboratory. You'll have the resistance box and also the carbon resistor. Resistance box is basically a wire bound resistor. If you open it up, you'll see wires, okay, wires, and you'll see a coil is made from that wire, okay, and that coil will be left on itself, okay, due to so that the inductance is eliminated. Okay, you'll learn about this in the upcoming chapters, but for now resistance box is a wire bound type of a resistor. It is made up of some alloys like nickel, we can also have constantan, manganese. So if you read the resistance box, you will read these names, okay, they are made up of those type of wires. Okay, coming to the second type, which is important for our discussion today, is carbon resistors. They, as the name suggests, are made from carbon and some binding agent. Okay, we won't go into the chemistry of that. Now this carbon resistors are first of all compact and inexpensive. This is their advantage over the resistance box. Resistance box, you have an entire box, right? It's bulky, it's heavy to carry and all of that. Here carbon resistor is just a resistor, small thing, okay, and here on that carbon resistor you'll have 4 colors, okay. These colors depict the value of the resistance, okay. You will have to decipher this code, you'll have to decode this code in order to know the value of that resistor, okay. You'll have 4 colors, color bands 1, 2, 3, 4, okay. From left to right you'll have different color. Color 1 will give you the first significant digit, first digit. Second, color 2 will give you the second digit, very simple. Color 1 first digit, color 2 second digit. Color 3 however will give you power of 10, some power of 10. Now you can have the resistor in kilo ohms. In that case this x will be 3, right? So that color will give you this power of x, okay, 10 to the power x. That x will be given by color 3. Color 4 is however the error in the measurement, okay. Remember that you have to move from left to right. So the last color over here is error, okay, tolerance or the percentage error in that resistor, okay. So suppose it is saying 300 ohms, but there might be an error of 5 to 10%, okay. So color 4 basically shows error. It might be missing in some cases. We'll come to that, okay. So remember this: color 1 first digit, color 2 second digit, color 3 power of 10, and color 4 is error. Okay, so this is how we'll decode this carbon resistor. Okay, here we are given 4 colors. We'll be finding the resistor resistance of this particular carbon what do you say, resistor. Okay, so the code for that is over here. This is a nice way of remembering it, but first of all let's go through the code. What does every band, every color represent? What does every color what is the number for every color? Okay, so we have different colors over here. For black the number is 0, brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, violet is 7, grey is 8, white is 9. Okay, now you are supposed to remember that, and there is a way to remember it. It's very easy. You just have to stalk at BB Roy's wife. Anyways, and finally we have also the tolerance, gold, silver, and no color. Okay, this will give you the percentage error in your this is basically for color 4. Okay, color 4 will be any one of them. Either it will be gold, silver, or there might be no color over there. Okay, so in that case you'll have different percentage wise error. Okay, and if it gold represents 10 to the power minus 1, if it's usually these colors are not used in 1, 2 and 3, but sometimes it might be used. In that case gold is minus 1, so if it appears as color 3, gold is 10 to the power minus 1. Appears as silver appears as color 3, it is 10 to the power minus 2. Please remember that. Okay, usually it does not appear in these 3 colors. This last gold, silver and no color will only appear in the percentage factor, but still on the safer side, remember that. Okay, so now the way to remember the digits for every color is Baby Roy's wife, and the keyword, or what you can call it, the catchphrase is over here. So BB Roy of Great Britain has very good wife. That is the phrase that you are supposed to remember. Okay, and yeah, I'm not ashamed as a physicist. BB Roy of Great Britain has very good wife. Okay, I'm complimenting, guys. Okay, so BB, so first B is for black. Okay, second B is for brown. So 0, 1, you can see. Okay, Roy, ROY, so red, orange, yellow, 2, 3, 4. So it starts from 0, remember that, and first color is black. Okay, black, brown, red, orange, yellow. Okay, so these many colors done. Okay, yellow. And off is not an important word, so we'll keep it at side. Great Britain, so great, GR for green. Okay, and then Britain, B for blue. 6, has is not important. These two words are not important. Okay, don't search a color for this off and has. Okay, so leave them out. Has very good wife. Okay, very, V for violet, G for grey. Now this first GR is for green. Okay, green. Okay, 5. First G is for green, second G is for grey, or you can directly remember GR of great, so that you can link it with green. Don't link it with grey. Okay, so first G is green, remember that, or grey is 8. Okay, you can directly remember that, great. Okay, and last is wife or white, which is 9. Okay, so BB Roy of Great Britain has very good wife. Okay, so and finally gold, silver necklace, because 5, 10, 20, 5, 10, 20. G, gold, silver, and N for no color. Okay, so that is how you'll remember it. Let's try our knowledge over here. We'll be not looking over there. We'll just do it via BB Roy. Okay, so here we have the color codes given from left to right: brown, yellow, green, gold. Okay, these are the color bands on your carbon resistor. Now let us find what is the value of this resistor. Okay, so first of all, brown. This is black. This is brown. It starts from 0. Remember, so 0, 1. So first digit is 1. Second color gives second digit. Okay, second is yellow. So 0, 1, 2, 3, 4. Yellow is 4, right? This is yellow, Y for yellow, and yellow is 4. Okay, it starts from 0, 1, 2, 3, 4. Okay, 4. And then we have multiplied by 10 to the power. Okay, third digit will give you 10 to the power something, right? So you have to multiply this with 10 to the power. It is some factor of 10. Okay, so this 2 digit and some factor of 10. So factor of 10, that will be given by the third color. Third color is green. Green, we know it is the first G, right? First G is green. So BB Roy of Great Britain. So G is over here. So 0, 1, 2, 3, 4, 5. Okay, 0, 1, 2, 3, 4 and 5. Okay, so 10 to the power 5. And of course, what are the units? The units are ohms, but you also have a error over here. Error in the measurement is gold. Gold is 5%, so plus or minus 5%. Okay, it can be slightly off by 5%. Okay, that is what we mean by the percentage error. You can check it. 1 is for brown, yellow is for 4, 10 to the power 5, 5 is for green, yes, and gold is 5%. Okay, so that's about it. Over to the next section. And this terminology is on battery, EMF and internal resistance. Now battery basic purpose is to create a potential difference. We won't go into the chemistry of that. You'll learn basically different batteries in your electrochemistry, in your chemistry lectures. Okay, so here battery creates a potential difference across your resistor, okay, and that will lead to current flow. Okay, so current will flow from higher potential to lower potential, higher potential at the positive electrode, lower potential at the negative electrode. Now you can see that inside the battery we have to move from negative to positive, right, from lower potential to higher potential. Okay, we are moving, charge moves from lower potential to higher potential. So in this case we have to, work should be done basically. Okay, so work should be done, meaning we can have some potential generate. Potential will be, so that EMF is a result of this chemical working of this battery. Okay, so EMF will be work done by charge. Okay, so this EMF basically, if you see, it has the same format as the potential that we learned in previous class, right? Potential is nothing but work done in bringing the charge from so and so to here and divided by the test charge, right? So work by charge, so that gives you EMF. EMF is nothing but potential. Okay, it is not force, although electromotive force it might say, but it's not force, it's a potential. Okay, that was some confusion while giving name to this terminology. Okay, so it was very back then, so they called it force, but it's actually a potential, not a force. So now let's come to the internal resistance part. That was about EMF, that was about battery. Now let's come to EMF. EMF is basically, we can say, a rating. Okay, the rating on the battery. Suppose you have a cell, on that cell it is saying 1.5 volts. Okay, so that is the power ratings, or sorry, not power rating, the voltage value when the battery is not in use. Okay, as soon as you connect the battery in some circuit, it will have its own internal resistance that will deplete the voltage across the battery itself. Okay, we see that when ideally the case should be whatever E that is there across the battery, that should appear as the voltage across A and B, right? But when we use it in circuit, when current is flowing in that cell, what happens is that there will be some internal resistance in the battery itself. Okay, this R is internal resistance of the battery. It's present there due to the chemical components of the battery itself. Okay, so when the charge are flowing through that battery, okay, what will they cause? They will cause collisions in the ions present in the electrolyte. So due to that, there is some internal resistance. Okay, and this internal resistance will decrease the actual voltage across your battery from E, which was the rating 1.5, minus some IR, the drop across your resistor. What is the voltage across resistor? IR, right? So this E minus IR across the resistor. Okay, so if you measure across the battery when it is working, it won't be 1.5, it will be something less. Okay, due to the internal resistance of the battery. Okay, so this is the actual voltage that appears across the battery. So voltage, you can say, is E minus IR, where R is the internal resistance, okay, across the battery. So when I is 0 meaning you are not using the battery, it's just there. Okay, so in that case there will be no resistance for the charge, since charge is not flowing. So this will be 0, I is 0, then this term will be 0, and you'll have V is equal to E. Ideal case, you're not using the battery. Whatever the rating is the voltage across the battery. Okay, so that's about internal resistance, battery and EMF. Let's move to the next section. Now let us learn about combination of resistors. Okay, just like we had combination of capacitors in series and parallel, here also we have combination of resistances in series and parallel. Okay, you might have learned this in your lower classes, but we'll go through it. Okay, and just an addition that the previous thing was, the previous two chapters were on electrostatics, so they give you an electrostatic component of the circuit which stores charge, which was capacitor. Now here we have resistance, which opposes the flow of charge, but it allows charge to flow. So that is your resistance. So your electrostatic give you your capacitor, electrodynamics or current electricity will give you resistors, and finally we'll have electromagnetic induction. There you'll learn inductor. Okay, so those are different components in the circuit. Okay, let's come back to series and parallel combination. So series combination, you know it, it looks like this, end-to-end connection of your resistors. Okay, here what happens is that whatever current is coming out through the circuit will go through R1 and R2. Same current I flows through R1 and R2. Okay, there is no branching for the current to split, so same current I flows from R1 and R2. Potential, however, will split across R1 and R2. R1 will get V1, R2 will get V2 depending upon their values. Okay, depending upon the value of the resistor. Higher resistor will take higher higher value of potential. Okay, will consume greater potential. So here in this case, R equivalent can be given as R1 plus R2. So this circuit can be transformed into this basically just with one resistance which has R equivalent value. R equivalent in that case will be R1 plus R2. You just have to add the two resistors to obtain equivalent resistance. Okay, equivalent circuit. So that in series combination. So in general, if you have more than two, in general, suppose you have n resistors connected in series. So in that case, you just have to add the n resistors. Okay, so adding n resistors will give you the equivalent resistance. Okay. Now coming to parallel combination, here you have two resistors which are connected across the same potential. So same potential across R1 and R2. Here the current was same. Here the potential is same because the two ends are same. Okay, same potential. The potential across them is V. Okay. Now current splits into I1 and I2. Of course, here the voltage was splitting into V1 and V2. V split into V1 and V2. Here I is splitting into I1 and I2 because there is branching. Okay. Now finally the equivalent resistance, the reciprocal of the equivalent resistance will be the sum of the reciprocal of this resistances. Or if you have two resistances, you can directly remember this relation that R equivalent will be product upon sum. Okay, which is R1 R2 upon R1 plus R2, R1 R2 upon R1 plus R2. Okay, and in general, if you have, in general, you can use the reciprocal formula only. The reciprocal of R equivalent will be the sum of the reciprocals of the resistances, individual resistances. Okay, now here let us try an example. Here we are supposed to find the equivalent, the net current which is coming out of this circuit. Okay, so I will be given as V by R equivalent. Right, we don't know the value, so we can break the circuit as simply transform it like this. Right, so for that we need equivalent resistance. So I in this case will be I is equal to V by V will remain same, which is 18 by R equivalent. Right, just simple. So we have to find R equivalent first. Now R equivalent, you can see that these two are in series and these two are in parallel, and the parallel combination is in series with 4. Okay. So R equivalent will be 6 and 3 in parallel, 6 and 3 in parallel and series with 4. So 4 series, write it this way, 6 parallel 3. Okay, these two are in parallel and that is in series with your 4. Okay, so 4 series meaning plus, 6 and 3 in parallel. I'll tell you a secret, 6 and 3 in parallel is always 2. Okay, that is something that you will learn in your coaching. Okay, that is a shortcut. Okay, so when you have 6 and 3, you can directly say it's 2. Okay, 6 3s are 18 actually, and this is 9, so 18 by 9 is 2. Okay, so 4 plus 2, here we have 6. So the R equivalent is 6 and I we can find from here. So 18 by what we have 6, which is 3 amperes. Okay, is that the answer? Yes. So 3 amperes is the answer over here. I hope that was super simple. Let's move to the next section. Joule's heating law, will be deriving a small expression for your power, and then that will lead us to heat. Heat is basically energy, so it is power times time, right? So basically if we assume that delta Q amount of charge moves through a potential difference of V in time delta T, this amount of work done, delta W, will be V times delta dQ, and if the time is very small, we can use differential terms, dW is equal to V dQ, and taking time rate. Okay, so a rate of change of work, and here we'll have rate of change of charge. Rate of change of work is power, right? And rate of change of charge is instantaneous current. Okay, so P is equal to V times I. Okay, so that is the expression for power. You can also derive the other forms using your Ohm's law. I is equal to, so you can use V is equal to IR, so that will give you I square R, or you can use I is equal to V by R, that will give you V square by R. Most useful is I square by R, and this is the power which is dissipated or which is consumed by your resistor. Okay, so that is the expression for power. Now Joule's heating, why is this heating caused? First of all, heating is caused majorly because of the collisions. Okay, so since the electrons are moving, the charge carriers are moving through the battery, through the entire circuit through the resistor, there are n number of collisions between the charge carriers and your lattice atoms, right? Atoms which are present in the resistor and even in the battery. Okay, so due to this, there is transfer of energy from your charge carriers to this atoms, right? And this transfer is usually manifested in increase in temperature. It increases the internal energy. Internal energy is a function of temperature. So it increases the temperature and there is heating. Okay, so that's the reason behind heating. Heat, as I mentioned, is a, if you see the mechanism over here, it is just transfer of energy, right? So this heat can be expressed as power times time. So power is I square R times T. Okay, you can also use the other form Vi times T, V square T by R. Okay, but that is the most useful one. Okay, so let us find heat which is developed here in the 6 ohm resistor in 2 seconds. Okay, let's try to solve this question. So we are supposed to find heat in the 6 ohm resistor. So we'll need current over there. Okay, so let us assume that the net current that is coming out of this battery is I. It will go over here, it will see branching, it will split into I1 and I2. Now since we have to find the current in the 6 ohm resistor, we need this I1, right? I square RT. Okay, then we can use I square RT and find it. Okay, so for that we need this net current. Okay, so that we can find what amount is going there and what amount is going there. Okay, so first we need to find I net. I is V by R equivalent. Now again, R equivalent will be, if you see this and this are in series, these two are in parallel, right? So we can say 6 and 3 in parallel, and this is in series with your 3, and this is also in series with 5. Okay, so 6 and 3 in parallel gives 2. You know that 6 into 3 divided by 6 plus 3, series means plus 3, and series again plus 5. So this is 8, this is 2, which is 10 ohms. Okay, 10 ohms. So we can find the net current. Net current is voltage, which is 20 net voltage. Basically this circuit is transformed into this R equivalent, and here we have 20, right? So I is equal to V by R equivalent. So 20 by R equivalent 10, which is 2 amperes. So 2 amperes is the current which is coming from your battery. Okay, now we can find using current divider rule the current in the 6 ohm resistor. I'll also do it some other way, in the logic way. The current divider formula is like this. So if you want to find the current in I1, you have to multiply the net current with R2, other resistor, upon the sum. Okay, so I is 2, right? The net current is 2, other resistor is 3, and the sum of them, 6 plus 3 is 9. 3 3s are, so 2/3. Okay, 2 upon 3 is flowing through 6 ohm resistor. This is the current. Okay, or we can also use logic. You see that the total the current is encountering over here is 6 plus 3. Okay, we'll just split it up in ratio. So total is 9. Okay, so total is 9. What amount should go here? First of all, 6 by 9. So we can do 6 by 9 once and 3 by 9 once. Okay, so this is 2/3, right? This is 1/3. Okay, so this is the resistance amount. Remember, right? Total is 6 plus 3, 9. So 6 upon 9 is in this branch, 3 upon 9 is in this branch. Okay, which is 2/3 and 1/3. Okay, basically you take the fraction. Okay, reduce fraction. So now these are resistances. Okay, this is 2/3 of R, this is 1/3 of R. Now where will be the current more? The current will be more where resistance is less. Here the current will be more, right? So we want to find for the 6 ohm. This is 6 ohms, right? 6 ohms. This is for 3 ohms. Okay, this logic might be difficult to understand, but if you get it, okay, you don't have to use the current divider formula. Okay, you don't have to remember this. Okay, so 2/3 amount of resistor in this branch, 1/3 amount in that branch. Now the current is inversely proportional to resistance. I is equal to V by R, right? You see, for the same voltage, parallel combination, current is inversely proportional to R. So here more current will flow. So more current will flow in 3 ohm resistor, right? Where the resistance, obviously logic, right? where resistance is less, current will flow more. Where resistance is more, current will flow less. Okay, so if we divide the current, we can also divide it into 2/3 and 1/3. So 2/3 amount of current will flow through this, and 1/3 amount of current will flow through your 6 ohm resistor. Okay, so 1/3 amount of current will flow through your 6 ohm resistor. Okay, and 2/3 will flow through 3 ohm resistor. Okay, so that is the logic over here, inverse relation. So 1/3 will flow, so 1/3 of I flows through your 6 ohm resistor, which is I is what? I is 2 amperes, so 2 by 3, same result. Okay, now you can find the heat. Heat is equal to I square RT. I square is 2 by 3, so 4 by 9. R is 6 and T is 2, so this gives us 3 2s are 3 3s are 4 2s are 8 8 2s are 16 16 by 3 is 5.33 joules. Okay, 5.33 joules, that is correct. Okay, so that was our answer, that was the logic, or you can use the current divider also. Over to the next section. Let us now come to grouping of cells. This is a complex topic, a little bit complex. Okay, so here we are only doing the formulae. We'll be deriving this in the next class, as I've told you. Here you are supposed to remember the formulae. Okay, so actually when we learn Kirchoff's law, you can come back to, over here and try to derive these relations. Okay, this and this specially. Okay, so for now let's go through them. Let's study the relations and let's use it in one of the numericals and let's find the answer. Okay, so case 1, we have series combination of different cells. Okay, so we are grouping the cells, combination of cells you can say. Okay, so here we have cells, each of EMF E, E, E and internal resistance small r, small r, small r. They are put in series and we have an external resistor R. Okay, so in this case the net EMF will be basically N times E. Okay, so the sum of all the E's, N E, 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 N times E, so N E divided by this resistance are all in series, so N times R plus M. Okay, so this was simple, V by R. So net V is all the batteries, and here we have all the resistances, internal resistances plus the external one. Sorry, this is not M, this is R, capital R. Okay, here also I want to check. Okay, this is correct, I think. So here if you replace, let me check that. Okay, here also it is R. Of course, it has to be a resistance. So here, if you change the polarity of M cells, basically this will become N minus 2M. Okay, minus 2M of the M cells which are reversed. Okay, when you reverse M cells, 2M you have to minus. Okay, so that is the opposing effect. But we won't be going in the detail of that. We might go during the derivation class. So for now, remember that M cells, if you reverse the polarity, you have to subtract N minus 2M. That will be the net EMF now. The resistance of course remains the same even if you change the resistor. Okay, it's still in series. Okay, now coming to parallel of the same cells are grouped in parallel. So we have ER, all of them are in parallel, and the net current over here will be E by the net resistance, right? These R resistance are in parallel, right? So parallel R resistance, equal resistance in parallel becomes R by N. N resistance in parallel becomes R by N. Okay, so here the net resistance is R by N plus this external one. Okay, so this was also simple, you don't have to derive it. So E will be the same because this is parallel combination, and here the net EMF across this will be E only. Okay, E remains the same. Here E is changing, right? It has become N times E. Here E remains same since it is parallel, and this is the net resistance. Okay, so these two are simple. Let's come to this one. This one here we also have the parallel, same type, but only difference is that the cells are different. Okay, cells are different, their internal resistances are different. Okay, so in this case we have to use this formula. It is summation EI. So this is for E net. Okay, keep that in mind. It is not for current. Okay, here we are finding only the net voltage. Okay, so it is E1 by R1 plus E2 by R2, so on up till En by Rn, N cells, and upon the sum of the reciprocals of the internal resistances, 1 upon R1, 1 upon R2. So we'll be solving one question on that. Okay, It's simple, the values are given, you are just supposed to substitute it. Let's come to case 4, wherein we are given a mixed cell. Okay, so here also in these 3 cases the batteries and the internal resistance are same. Okay, case 1, case 2 and case 4. Here only there is a difference. So case 4, E and R same, but here N cells are in series and M are in parallel. N are in series, M are in parallel. So the net EMF will become N times E, right? In parallel it is not changing, in series it is changing, which is NE. Okay, so you can go back and get back this result, right? So this internal EMF becomes N times E. Now the resistance, that is the question. If you see, the cells are in parallel, so N times R and NR are in NR in every branch you will have. So those NR are in parallel, so NR in parallels becomes by M, right? Since there are M branches, so NR divided by the number of branches, which are M. Okay, and of course the output resistance is also there. Okay, so we're just brushing past it. Don't worry if you are not getting the point. Okay, if you're not understanding it very deeply, you're just supposed to know the formulae. Okay, so here we are just brushing on to them. Okay, I is now the net EMF divided by R equivalent, so that is I, and this will be maximum. The power derived by the circuit will be maximum when I is maximum, I maximum. When I is maximum, this two should be equal. Okay, this is a condition that we obtain from differentiating. We equate the first derivative to 0, and that gives us this condition. Okay, we'll speak about it more in the derivation class. So this denominator, these two terms should be equal for current to be maximum. Now let us come to this. We are given E1, E2, E3 in this type of a circuit. R1, R2, R3 all are equal to the output resistance, which is 1 ohm. So you are supposed to find E net. Okay, so we have 3 resistances. So let's use the formula for this type of arrangement, which is this: E3 R3 upon 1 upon R1 plus 1 upon R2 plus 1 upon R3. So if you see R1, R2, R3 all are 1, so let's not write them, you can directly do it. So E1 is 3, E2 is 2, E3 is 1, and we have in the denominator we'll have 1, 1, 1, right, divided by 1, 1, 1, so that does not make any difference. So here we'll have 3 plus 2 plus 1, 6 divided by 3, which is 2, right? 2 volts is your answer. Okay, it will be 2 volts only. Yes, 2 volts is your answer. So that is about grouping of cells. Remember the formula, note it down somewhere. Okay, so that's about this section. Over to the next one, to an interesting and important part of this chapter, which is the Kirchoff's law. You might have heard it. You will be using this to solve very complicated circuit. Okay, so once you learn this, you will be able to solve any complicated circuit and you can flex it among your friends. Okay, Kirchoff actually was also a student when he discovered this law. He was given actually homework from his school, and he just found the sums very difficult, the circuits very difficult to analyze. So he came up with his own rules and it did work, right? So take your homework seriously, you might have your own law someday. Okay, so let's come to Kirchoff's law. We have the junction and the loop. Okay, these are two terminologies which we have to define before we go to the Kirchoff's law, because the first Kirchoff law is Kirchoff current law, which is the junction rule, and second is the Kirchoff voltage law, which is dependent on the loop. Okay, so let us learn what is junction and loop. So junction is a point where 3 or more conductors meet. Okay, so you have wires, and junction is a point where you can assume a crossroad. So 3 or more, okay, 3 or more wires are meeting at that point. Okay, so it's a crossroad basically. So you should at least have 3 or more than that for a junction, for a point to be a junction. Okay, let's come to a loop. A loop is basically a closed conducting path. Okay, so here if you see we have a loop, right? If you move from, let's take this path A, B, C, D, A. Okay, these are 2 batteries and this is a loop starting from A coming back to A. Okay, that is a loop. Okay, so these are the terminologies that we need to know. Let's come to Kirchoff's law, the 2 laws which we will be using. Okay, it was based on very simple things. Okay, he found it out it was based on very fundamental things like conservation of charge and the conservative nature of electric field. Okay, let's come to the first law. It is Kirchoff's current law, okay, which is also known as the junction rule. It says that the sum of current at any junction is zero. Okay, so the amount of current that is entering a junction should be equal to the amount of current that is going out of the junction. Okay, so there should be no accumulation of the charge at the junction point, right? The amount of current that is coming to the junction should be the amount of current that is going out of the junction. Incoming current should equal outgoing current. Okay, so this is based on conservation of charge. As I told you, there should be no accumulation of charge. Charge cannot be created nor destroyed. So whatever charge is coming should go out. Okay, so here I3 should be equal to I1 plus I2. Okay, so I3 is incoming current. If you see, it is splitting up into I1 and I2. So of course it should be equal to their sum. I1 plus I2 should equal I3. Okay, so if this was less, then it means that charge has accumulated somewhere or charge is destroyed. Okay, some amount of charge is lost, which cannot happen, which is violating the conservation of charge. Okay, so here whatever current is incoming should be at a junction should be equal to the outgoing current. Let's come to the KVL rule. So that was very simple, right? This will help us solve complicated circuits. Okay, it will become more clear when we solve a problem related to this. So second law, Kirchoff's voltage law. So sum of the potential differences along a loop is zero. Okay, so this is very common, full of common sense, right? So the potential difference across an entire loop will be zero. If you start at A and come back looping around back at A, of course the potential difference at point A minus point A is zero, right? So sum of potential difference across a loop, when you go in a loop, if you keep on adding the potential differences, that will be equal to zero. Okay, so why is this useful, you are saying? Because this will give you one of the equations. So if you start from here A to A and come back to A, this will give you equations regarding these components in the circuit. Okay, we'll see it in a question. This is due to conservative nature of electric field. Okay, we know that electric field is a electrostatic force is a conservative force, Coulomb force is a conservative force. So and electric field is itself conservative. Okay, something that we learned in previous two chapters. So this voltage law is a effect of it. Okay, is a result of that. So electric potential should be defined at all points for this to be valid. That is also something that you should remember, that potential at every point should be defined in order for this law to work. In electric circuits, it is usually defined. Okay, the two conventions, which is the most important part, this is the problem solving part, this is the theory and the concept behind, the idea behind this Kirchoff's law. But the thing that will help you solve this question are these conventions. Okay, the only two conventions. Okay, one is when you're moving through the source, when you're moving through the battery, one, and second when you're moving through a resistor. Okay, let's see them. So when you're moving through a battery, through a source, a battery, so source E, which is the EMF of that battery. So if you're moving from the negative plate to the positive plate, there is gain, right? You are going from negative potential to a high potential, low potential to high potential, there is gain. So we use positive sign. So positive E, plus E we will say. And if you are moving from the positive plate to the negative plate, if you are moving in the other direction, you will use a negative sign, minus E. Okay, this is convention number one when you're moving through source. Now second, when you're moving through resistor, how do you define what is positive and what is negative for a resistor? Resistor is a linear device, right? It does not have polarity. Okay, we discussed in limitations of Ohm's law. Okay, resistor is a linear device. So when you're moving through R, you look out for the direction of current. If you are moving through R in a direction which is same as that of the electric current, there will be loss. Why same direction is loss? Because electric current flows in the direction of decreasing potential, from high potential to low potential. So if you're moving in the direction of electric current, you're moving from positive to negative, which is a loss. Okay, so if you're moving in the direction of current, you're moving from higher potential to lower potential. So that is a loss. Okay, so we are using minus sign for it. Again, these conventions were just fixed by your textbook. You can flip it around, okay, but be careful while flipping it around. If you're flipping this, flip this too, okay. You just don't flip one of them, okay. So that or just follow this blindly. Okay, this works. Then we have, if you're moving opposite to the direction of current, now if you're moving opposite to the direction of current, it is from a lower potential to higher potential, right? So that will be a gain, and you'll say plus IR, and in this case minus IR, the potential. Okay, we can apply this Kirchhoff law over here. We are choosing the path from A to B. Let us find the potential difference VAB. So VA, so potential at point A, let's say it is some VA. So then we are moving in the direction. Now we are moving from A to B. Okay, we are in the direction of current. You can see that current is also from A to B. We are also moving from A to B, and this is a resistor element, same direction as that of current, minus. So minus, what is the drop across resistor? IR, right? And finally to point B. So this should equal the potential at point B, or you can say VA minus VB, which is your Ohm's law, is IR. Potential difference is IR. Okay, this is for a simple path. We'll do it for a more complicated circuit that will open up your mind. Okay, so that's about Kirchhoff's law, the theory and the conventions behind it. Let's move to the question. Supposed to find the current in different branches. This is a question based on your Kirchhoff's law. The question will be of similar types only. You will see multiple batteries in a circuit, and you will be asked to find current through a particular resistor, or maybe through different branches, as in this case. Okay, so let's find it out. So first of all, what we are supposed to do is to name this. Okay, name the corner points so that we can choose a loop. Right, so we'll say this is point A, this is point B, this is point C, this is point D, E, F. Okay, now we can choose loops. Now this is all up to you. Okay, you can do it in your own way. Okay, I'm choosing current I1 to be coming out of this 2 volts resistor. Okay, and now the I1 will come to point B. Okay, I1 will come from this battery to this point B. Now it will split into I2 and I3. I'm saying that. Okay, so I2 goes in this part of the circuit. Okay, and I2 and I3 again they become I1 over here. Okay, there is no accumulation of charge. I1 is going inside, I1 is coming out. Okay, I1 is going inside, I1 is coming out. Okay, it is splitting into I2 and I3. So here I can write the equation I1 is equal to I2 plus I3, right? Or from here also you can see this is I2 plus I3 is I1, right? Or I1 is splitting into I1, I2 and I3. Okay, so this is from KCL. Okay, so here you are supposed to form this type of equations, solve them and obtain the currents, different currents. Okay, so let us choose a loop. We'll choose path or loop, you can say. We'll move from here. This loop we will choose. You can choose any loop, okay, provided you follow the convention. You'll always end up at the right answer. Okay, you can also I started I1 from here. You could have brought current from here and split it into 2. That is up to you. Okay, you will get to the same answer. That is the beauty of this. So we are choosing this path F A B E F. Okay, F A B E F. Now from F to A, now we will be moving along this path, and we will be using KVL, sorry, the voltage law. Okay, so we are moving around the loop, and we'll equate this voltage to 0. Okay, so starting from point F, moving to point A, F to A, right? First thing, so we come across a source, right? And we are moving from negative to positive, gain across the source, gain, right? So plus 2 volts. Then we move from A to B. We have a 4 ohm resistor. I1 is the current moving, and we are moving in the direction of the current, right? In the direction of the current. So minus I1 times 4, I1 times R, right? I1 times R. Now we are moving from B to E. So we are moving from this source, through this source, negative to positive. So again plus 4. And finally we are moving from E to F. Now E to F, if you see, we are moving in the direction of the current again. So minus current is I1 only, I1 times 2. So this is equal to 0 because we are back at point F, right? So this will give us 6, and this will give us minus 6 I1 is equal to 0. So I1 is nothing but, simply you get the answer, I1 is nothing but 1 amperes. Okay, I1 is nothing but 1 amperes. Actually, I had done this differently on my book, and I'm doing it differently over here, but I'm getting the same answers. Okay, so here in my book I had done, I had drawn out current from this cell and split it into I2 and I3. Okay, here I'm getting the same answer, I can confirm. Okay, so it is up to you what path you choose, uh, what loop you choose, and what current you choose. Okay, so now let's come to this loop. Okay, we'll only choose the small loop. You can also choose the bigger loop, A, B, C, D, E, F. Okay, you can also go that way, uh, but we'll choose only the small ones. We'll go from B, C, D, E, and back to B. Okay, B, C, D, E, back to B. Okay, now let us find that. What do we have? So beginning from point B, we have we are moving in the direction of current I2, so minus I2 times R. Okay, in the direction of current negative. Now we are moving from positive to negative, again minus E minus 6. Okay, moving in the direction of I2, again here also we are moving in the direction of I2. I2 is moving like this, right? In the direction of I2, minus 2 times of I2, right? So I2 times 2, I can say IR, right? And finally here we are moving from positive to negative, again negative, minus 4 is equal to 0. Okay, so what do we get? This will be minus 10 and this will be minus 4 I2. Okay, that is what we get. So I2 is more minus 4 I2 times minus 4 I2 is 10. So I2 is minus 10 by 4, or we can say 2 by 5, 5 by 2. What am I saying? So this will be minus 2.5 amperes. Okay, minus 2.5 amperes. Am I missing something over here? Okay, so yes, this is correct, minus 2.5 amperes. So why is it negative, first of all? Okay, so that might puzzle you, that current has come out to be negative, right? So it's only negative because our convention is not good. Okay, negative means that it is opposite to the direction chosen. Okay, opposite to the direction chosen. So where is our I2? So I2 is along this direction, right? So it actually in this circuit it will be flowing in this direction. Okay, we have chosen the wrong direction, that's why it is showing a negative sign. Okay, so that is the meaning of negative sign. Again, you get the correct answer, only the direction is reversed. Now you get I1, I2 you got. You can easily find I3 from here. I3 is basically I1, so you can use this relation, I1 is equal to I2 plus I3, right? So I3 will be I1 minus I2. Okay, I1 is, if you see, I1 is 1 amperes, and minus I2, minus of minus, place it with sign, so that will be plus 2.5, so that will give you 3.5 amperes. Okay, 3.5 amperes coming out from here. Okay, I3, this is 3.5, and that will be 2.5. Okay, the net current I1, where is that? I1 is 1 amperes. Okay, so this is the last part of this chapter, wherein we will be discussing the measuring instruments. There are 3 of them, 2 of them are here, one more we will discuss, and we will be wrapping up with this class. So cheers to you if you made it this far. Good for you. Okay, so let's begin with this wheatstone bridge. Okay, and here we have meter bridge. So wheatstone bridge, it is one of the measuring instrument. We can use it to measure unknown resistances. Okay, how does it work? It is based on the principle of balanced point. Actually, you can use this, solve this circuit via your Kirchoff's law that you have just learned, and obtain this condition. Okay, here PQRS are resistances, and there is a galvanometer, a device that basically measures current, right, detects current, is connected between A and B. Okay, here is some cell, okay, battery, and the balance condition is that, balance condition basically means that a condition at when there is no current flowing through the galvanometer. Okay, so this will be at a specific case when these ratios are balanced. Okay, P by Q is equal to R by S, then the potential at this point will be equal to potential at this point, and there will be no current flowing through the galvanometer. The galvanometer will not show any deflection. Okay, so in that case, this two the resistance in these branches will be in the same ratio. P by Q will be equal to R by S. Now this can be used to find the unknown resistance. Suppose your S is unknown resistance, then what will you do? You will vary R, okay, vary R till you see no deflection in your galvanometer. Okay, so S is unknown, you will vary R, vary resistance box R, and see look for this deflection point becomes 0. Okay, when does deflection becomes 0? When does the deflection current becomes 0? Okay, when the deflection in the galvanometer is 0 for a certain value of R, keep that fixed. Okay, now you know the value of P, Q, R, and you can find the value of S using this relation. Okay, this is valid only at the balance point, remember that. Okay, you can derive that from using Kirchoff's law. You can apply Kirchoff's law over here and you can reach to this condition. Okay, now as I told you, it can be used to find unknown resistance, and how also I told. And here you can also interchange this cell. Cell can be placed in place of galvanometer, and the galvanometer can be placed around like this. Okay, it's the same circuit, there is no difference over there. Okay, so cell and galvanometer, if they are interchanged, it's the same circuit, it will act like the same wheatstone bridge. Okay, there are no differences over there. Okay, so one more thing which is based on the very concept of wheatstone bridge is your meter bridge. Okay, basically gets its name because this is a meter long. Okay, AB, so we just have a wire has its own resistance, right? So we have a 100 centimeter long wire or 1 meter long wire. Okay, and we have a galvanometer over here, two resistance boxes R and X. Now X is that unknown resistance, we can find it out using the same concept. You just have to slide the wire at on the wire. Okay, you have to slide a jockey, this is called jockey, and you have to slide it over the wire. Okay, and at a certain point on the wire, this galvanometer will show 0 deflection, the current will become 0, which means that the resistance of this wire, this section of wire, is equal by this, and this by this will be in the ratio, right, will be in the same ratio. The balancing condition, when Ij is 0, this by this will be equal to this by this. Okay, so that is the same ratio that we can use. Now one more condition over here is that since this wire is meter long, your resistance is directly proportional to length, right? If the area of the wire is uniform, rho is R is rho L by A, right? So rho and A are constant, area is uniform, A is kept constant. Okay, area is constant, rho of course for a given material is constant, then resistance is directly proportional to length. Only changing factor for resistance is the length, right? So as you change the length, the resistance of this branch will change. Okay, so that is the idea over here also, where we are changing R. So instead of R, we can change the length, right? Length and resistance are directly related over here. Okay, so we are changing the length, meaning we are changing the resistance up till we reach a balance point. Okay, and at that balance point, this condition is satisfied, and you can also write it, since this ratio is equal, you can just take this to this side. Okay, and so R by X should be equal to this because resistance is directly proportional to length, right? So R, this is the resistance of this branch, right? R is the resistance of this branch. Sorry, R is the resistance over here, what I'm saying. So R is the resistance over here and X is the resistance over here. Then this resistance is proportional to this length, right? It's proportional to L, and this resistance will be proportional to 100 minus L. This is 100 minus L, right? 100 minus L. Okay, so resistance proportional to length, you can see it. Okay, so using only that condition, you can use this condition. Once you know the balancing length, once you find the balancing length, you can use this condition, and find the value of unknown resistance. So that's about meter bridge and wheatstone bridge. Over to the last one, which is the potentiometer. Coming to the final part of this chapter, which is the potentiometer, the last measuring device that we will be discussing today. So it can be used to measure and compare, or compare EMFs, and also measure the internal resistance of a cell. Okay, so how does it do it? Basically, I'll go briefly over it. Okay, we'll study this relations when we come to the derivation part in the next class. Okay. So here we have a potentiometer, we have this wire AB which is stretched out. Okay, it's stretched like this. These are usually metal, so this do not contribute to any resistances. Okay, these are metal parts, metallic strips you can say, and this is the wire running through that. Okay, you don't have to put it in one line, you can just wrap it around, right? So here we have a battery, and we also have a key you can plug in, and the circuit will be on. Okay, so here we have an element across which we want to measure the potential drop, the voltage. Okay, so we want to measure the voltage between V and B. So here also we have a jockey, and we'll be sliding on this potentiometer wire. Okay, so at a certain point on this, we will get the this current to be equal to 0, which means that the potential over here across VAB is equal to potential at VAP. In that case, this current will become 0. Since the potential is equal, no current will flow. So this potential across these 2 points A and P will be equal to A and B. In that case, your current, galvanometer current, deflection current will be 0. Okay. Now the idea behind this is that your wire has a uniform cross section. So in that case, we know that the resistance is directly proportional to length. Okay, if the wire cross section is uniform, this area is uniform. Okay, and since V is equal to IR, your voltage is also proportional to length. Okay, so you can replace it as V is equal to phi times L. Okay, phi is a constant. It is called voltage gradient. Okay, gradient because it is voltage per unit length. Okay, phi is defined as V by L. Okay, this is an important quantity, you should remember it. Phi is V by L, voltage per unit length. Okay, so basically this voltage V will spread out on the entire of the wire. Okay, so here suppose this is 4 volts, so it will start at 4 volts over here, and here it will become 0 sort of. Okay, so here phi will be 4 volts divided by the length of this wire. Okay, so that is how you can find phi, and using phi you can find the voltage across these 2 points. How do we do that? Since your voltage V corresponds to length L, since this voltage V will drop across this length L, this voltage AP has some length X. Let us suppose this length AP is some X. Okay, so we can say that you will find this X experimentally, right? You will slide your jockey over this wire up till this deflection becomes 0. Okay, so you will find this X experimentally. So you can find VAP. Now you can just cross it over. So VAP will be V by L times X, V by L times X, which means VAP is phi times of X. Okay, so phi you can find as V by L. Okay, first of all you will be given V and the length of the potentiometer, so V by L, that way you can find phi. X you will determine experimentally. Okay, you can also find it theoretically using different means. Okay, in other circuits, and phi times X will give you the potential drop across the element. Okay, so that is how you measure potential using potentiometer. Now 2 other applications will be comparing EMFs. So since it can measure EMF, it can compare EMF of 2 cells, right? It can measure EMF of one cell, then other cell, and then compare those 2, right? So here we have 2 cells, E1 and E2. In this case we had only one resistor element. Here we have cells E1 and E2. One time at one point we will be using one cell. Okay, so first we'll plug in this cell, and then when we are plugging the other cell, we'll remove that, we'll plug this cell. Okay, so we'll find the balancing length for both of them, L1 and L2, and this is the relation that holds true. Okay, so E1 by E2 will be L1 by L2. Okay, so if you know the EMF of one cell and the balancing length of both cells, then you can find the EMF of other cell. Okay, So that is how you can compare EMF using, it's the same concept over here. Basically you are finding potentials, right? Potential of this cell first and this cell first using the balancing law, okay? And if you see V is over here, E1 is phi x, right? E2 is also phi x2, okay? So those two are cancelling, you have L1 and L2, okay? Finally, we can also find the internal resistance of a cell using this potentiometer. So what we do is first we find, we have this arrangement, okay? The above part is same as this, okay? The only thing changing is over here, this part, okay? We have a cell, we have a resistor, and finally we have some output resistor and a switch. This switch is important. So first of all, we'll not close that switch, okay? We'll keep that switch open, so then no current is flowing in this part of the circuit. So in that case, what are we measuring? We are measuring EMF of the cell, okay? Since no current is flowing, the battery is not under use, we are measuring EMF, okay? So in first case, we'll measure L1, which is the EMF of the cell. Then we'll close this switch. When we close that switch, some current will be flowing in that circuit. Remember that there will be no current across the galvanometer at the balancing point, of course, but there will be current when you close the switch. There will be current inside the cell, okay? So some amount of potential will drop across this internal resistance, okay? So in the second case, when you close the switch, we are measuring some less potential meaning it's the actual potential, the cell under action, right? So we get in first case we are balancing the EMF, in the second case we are balancing the voltage across the battery, okay? So using this relation, using L1 and L2, we can find the internal resistance of the cell. R, small r, internal resistance will be given as capital R, this R, times L2 minus L1 minus 1, L2 upon L1 minus 1, okay? So that's all about this chapter. I hope you really enjoyed it and you were able to understand this within an hour. Of course, a lot of practice is required, especially on Kirchoff's law and this measuring devices. It's not just a matter of hours. You can go and practice a lot now and strengthen this topic. You can understand it within an hour, but to become good at it, you have to practice a lot, okay? So that's the aim of this series, okay? To deliver it to you in a concise manner so that you can go on and practice it and improve your topics, okay? So that's about this video. I hope you really enjoyed it. If you want to follow this series, do consider subscribing. We'll be doing this for all the chapters that are out there in your 12th standard and in your 11th standard once we are done with 12th standard. And if you wish to follow me in the next video, which will be the derivations from this particular chapter, do come back on 2nd of October, 2nd of November, I think. So that video will come out on 2nd of November. So yeah, that's pretty much what I wanted to say, and keep enjoying physics.